So the next allotrope of carbon is fullerene. So we have been discussing about the graphite. When you look into the structure of graphite, or as we have already discussed, they have layered structures. Now let's take the graphite, and if you take the graphite, in presence of electric arc and in inert atmosphere, as you are supplying some of the energy, rearrangement can happen here. So after rearranging, when you consider the sheath layer on electric arc passage, they are actually getting converted to give either a sphere or a tube, and this is said to be as fullerenes. So when you consider the fullerene, they can be in the form of spheres or a tubes. If it is in the form of sphere, then it is called as buckyballs, or it can be nanotubes. So these buckyballs or nanotubes are the most purest form of the carbon allotrope. So that is obtained basically from the graphite. Graphite has a layered structures. Take the individual layer, which is called as graphene. So on passing the electric arc, they are converting into some other forms. And now you are obtaining the structure which is called as fullerenes. So when you consider the fullerene, let's consider the buckyballs where you have the sphere. And in this case, either the sphere can have all the rings can be hexagonal, or when you consider the sphere, they can even have two types of ring, and one can be pentagonal, where you have 5 carbons joined to give the pentagon shape, and the other ring possibility is formation of hexagonal layers. So whenever you consider these structures, this is the pentagonal ring, and each pentagonal ring is surrounded by the hexagonal ring. Whereas when you consider the hexagonal ring, they can be surrounded by hexagonal rings and as well as the pentagonal rings. So the rearrangement can happen in such a way that bones are broken, and again they are rearranging to give you the 5-membered rings. Now what about the hybridization here? Again, when you consider the individual carbon, let us consider one carbon. So consider this carbon, just like in the case of graphite, as the carbon is again making 3 covalent bonds. You have 3 bonds making to get the structures. So 3 bonds are formed that indicate carbon should make available of 3 unpaired electrons, then only 3 bond formation is possible. Same, consider carbon in its ground state, you had 1s2, 2s2, 2p2 is the configuration. We are just focusing the valence shell electrons. So let's represent the 2s and 2p orbitals, where 2s contains 2 electrons and that are in the paired condition, and 2p you have 2 unpaired electrons. Does the carbon require to excite? So the answer is yes, because again in this structure carbon needs 3 unpaired electrons, but in the ground state they have only 2 unpaired electrons, and the remaining 2 electrons are in the paired condition. So excitation is must here. After the excitation, say the electron get excited into the 2p orbitals, so you are having the 2s and the 2p orbitals, where now you are getting 4 unpaired electrons. Again in this case also you need only 3 bond formation, so that among the 2s and 2p, the 2s and the 2p, among the 2p you have 3 orbitals, but you need only 2 electrons from the 2p because you are already taking 1 electron from 2s, and thereby you are taking 3 unpaired electrons, and to this system the next carbon will donate its unpaired electrons so that there is sharing happening. Now you have 3 CC bond formation and 1 electron is extra. Therefore, when you consider the hybridization, as the carbon in the excited state is utilizing the electrons present in the 2s and the 2p, only 2 orbitals from the p is utilized. That indicate the hybridization is sp2. So these are the hybridization observed in the case of allotropes of carbon, diamond, graphite and fullerenes. Now we'll see into the combined structures of carbon, that is carbon compounds. Thank you.